Okay, so thanks a lot. Thanks for joining this this session now. The new this talk is entitled Eco-Friendly 6G, just to trying to give a kind of different perspective to this new sustainability topic that looks like the new trend for Europe and let's say for all upcoming research items. So basically the title, as you can see here, is Integrated Sustainability with RIS and Integrated Sensing and Communications Innovations. So I'm Vincenzo SCIANCALEPORE from NEC Europe Lab. We are located in Heidelberg in Germany. Basically, I'm principal researcher leading the research team on, as I said, RIS, so smart surfaces, reconfigurable intelligent surfaces, or IRS, how you want to call it. And now we are migrating to this new topic called ISAC or JCAS. I'll try to give you a very brief introduction about all of this, and then we'll see what we can do, how we can exploit the RIS and the smart surface concept within this new ISAC landscape and ecosystem. So basically, as you can see here, 5G networks, we are there now. The classical communication paradigm say that the propagation environment is seen as a black box. So we may try to develop, to design advanced transmission techniques to overcome sometimes this kind of time variant problem in the channel quality. And let's say most of the time we aim to get the kind of line of sight between transmitter and receiver. Now we are trying to move to the new topic, let's say to the new generation of wireless networks, which is the 6G, where we envision those three S. So the smartness, the scalability, and the sustainability. Smartness, because now we would like to create a kind of advanced control on the propagation environment. What has been seen so far, envisioned so far as a black box, now can be something that we can control. We can pose now the control on the radio propagation environment. And I will show you how to do that. Scalability, because we would like to get a kind of scalable network. And this is directly linked to the sustainability part. That, as I said, is one of the novel topics that can really bring low cost, limited cost, while implementing new infrastructure and also network features. I like this picture out because here you can see this nice concept called ISAC, or Integrated Sensing and Communication, or JCAS, Joint Communication and Sensing, as you want to call it. Then I try to put it there, as you can see, this new topic called generative AI. Why generative AI can assist, as I put there, ISAC? Because nowadays, with AI, with generative AI algorithm and concept, we can start interpreting the data coming from the sensing world, from the sensing part. So for us, as we will see in a few slides, the idea is to start integrating whatever is already there in the infrastructure, in the communication infrastructure with the sensing part. So try to put together, to fuse the data collected by the sensors, while exploiting the existing network. AI, and let's say in particular generative AI, can help on that, can start really interpreting and get all this data, try to reduce even the error that we can get while transmitting data. It can, of course, try to reduce the complexity of our existing infrastructure. Unfortunately, today, I'm not going to talk about generative AI, perhaps in a different talk. So I will just try to focus on the RIS for ISAC. Let's start just to give you very briefly some definitions. Let's start from sensing. As you can see here, the idea is just to have a kind of transmitter and receiver sending data. And then we can get, let's say, all these signals scattered of those objects, and then we can collect and exploit all this information to understand, to get additional information regarding what we call sensing. So basically, we have radar-like sensing. We may have also non-radar sensing. And one of the main concepts there is what we call CAS, or communication assistance sensing. where, let's say, for instance, the base station or the transmitter can actively senses the target through what we call device-free wireless sensing, and simultaneously transmit all those useful information to the final end user. On the other side, we have what we call then positioning. So we move from sensing, which is a general concept just to use to exploit the sensing capability of some devices, to what we call positioning. Basically, there we have a kind of like to estimate the position of a connected devices. So here, this means that the device is connected to our network infrastructure, and then we move to what we call localization, where we can even try to get the position of a passive target. Of course, in this case, what we try to do is also to estimate like orientation, the speed of such device. And then we move to the final, let's say, definition of JCAS, as I said before, or ISAC. Basically, is the idea behind all these new nice concepts that we would like to reuse the existing hardware, so save, as you can see there, resources versus like deploying two different independent systems, and deliver additional services. What's those services are what we call sensing, what we call localization, what we call positioning. And then we have the last concept of SAC, or SAC, which is the sensing aid communication, where we can like reuse, exploit, and leverage on the information that have been obtained from all these sensing or sensor networks in order to enhance the efficiency, reliability of our communication. As you know, ISAC is getting this momentum now. We have different European projects, European funded project on this concept, on ISAC or JCAS. We have also the standard moving toward that direction. So we have, since a few months, a new ETSI, European Standardization Group, on ISAC called ETSI ISAC. And we have also like 3GPP, like in RAN, expected to start a new study item within the release 19 on ISAC. And then, as you can see, I just put a couple of examples, like one way Ericsson, but of course there are other like Nokia and so on, also deploying solutions and hardware for ISAC. I just tried to put here a nice slide summarizing what is like expected as standardization roadmap for ISAC. Basically, we are here. After the preliminary specs, the ETSI ISAC group was launched, as I said, a few months ago, and now is within the first 2 years phase, while 3GPP will start like in less than 1 year with this release 19, where there will be a new study item only on ISAC. The idea for 3GPP, as you can see here, this is something that I got from the workshop, the 3GPP workshop on release 19, that they would like to get what we call joint sensing and positioning in smart factory, so in a factory code. Basically, like just to briefly summarize what you can see here, there are several use cases, but the idea would be to reuse, again, the existing infrastructure within that specific smart factory to provide additional service. And I have a nice video later to show you how that can be possible using our existing hardware. So for us, this, what you can see there, 5G system nodes, could be the smart surface, could be the RIS. Of course, what's the problem here? Is that the communication infrastructure that is already in place might be not able to support this kind of joint communication. So we really need to find a solution, and the question would be how to power a sustainable revolution in order to build this ISAC within what we already have. The main questions that you can see here could be how to track many connected UE plus passive object targets, both static and mobile, and how to perform ISAC in a distributed way. So with many distributed base stations that can act as transmitters, receivers, supporting monostatic, bistatic, multistatic sensing. How we can do that in a sustainable way? And we have several options, but in my opinion, the one that you can see there, marked as green font, can be the one that can really bring sustainability within our net, which is the Reconfigurable Intelligent Surfaces. Envision seen as passive nodes that can really add within our existing network the control on the propagation environment, and in parallel can really deliver additional service. And this is the answer from NEC, which is called NEC Smart Surface, which is a real prototype that we've been devising and testing now since almost a couple of years. This is the new version called Smart Surface 2023. And basically, as you can see here, is a reflector array working at 5 sub-6 gigahertz. In this case, it's 5 gigahertz with 16 by 16 antenna elements. Basically, the idea would be to have a 3-bit quantization here for the phase shift, and then being able to configure each of those antenna elements independently in order to steer the reflected beam toward the direction we decide. Basically, I can briefly summarize what you can see here. We have for each of those antenna elements an RF switch. So in this case, we have 256 RF switches. We have different delay lines such that we can apply a specific phase shift for each of those components or cells. And then once the signal comes through the antenna feeder, the RF switch is activated for one selected delay line. Then the signal goes only into one of those delay lines that are properly designed in terms of length. And then it's just fed back through the same RF switch to the same antenna feeder in order to control the wavefront once the signal has been reflected. Doing this for 256 elements will really give you like a final control on the reflected signal. In our case, we selected 3 bits. So basically, we have like up to 8 different states per cell. And one of those states, you can see here, we have a kind of resistor, and we call it absorption state. This means that once we set all those elements for the last state, the RIS is kind of absorbing the signal without reflecting it. So this is, again, our last design is working at sub-6 gigahertz. So the only difference between the 5 and 3.7 is the interdistance. At the moment, we are working on something like different, but this one is like keeping the interdistance equal to lambda over 2, as usual, just to avoid mutual coupling. But theoretically, also Marco and other professor, we are working on how we can really go for like a shorter, for a limited interdistance among those elements. The 3.7 version, of course, will have a different interdistance, but the design will be practically the same. And this is our controller or control board that is just attached behind the RIS. So this is, again, very limited power board, and we can even change the configuration every 35 milliseconds. So this can be a kind of sustainable answer to our question. So we can get a passive sensing node with very limited, or what we call nearly passive smart surface, with a very limited power consumption, changing the reflection angle of the impinging wave. I think we can go quickly here. This is just, again, the definition of what is an RIS. As you know, it's just a way, man-made 2D nearly passive surface where we can control. We start very simple. So now we are just controlling the reflected beam. Basically, yes, compared to like a classical normal material, here what we are doing is just to change, to steer the reflected beam toward the direction we decide with, I would say, quite wide angle. And this is a nice definition, because here you can see what is an RIS from the network perspective. Basically, as you can see, it's a new type of system node with reconfiguration capability. So we can really integrate, we can start thinking how to integrate this new node within the network architecture and the network existing network infrastructure. And I have a nice slide also connected to what Intui was showing this morning on how we can improve, how we can even start thinking how to integrate such new nodes within the ORAN architecture. And basically, yes, here is what we see as sustainable, having a kind of passive node that can be directly integrated within the network infrastructure. Let's see, let me show kind of like analysis, cost analysis on these devices, just to show that, to prove that there is kind of sustainability while approaching this new technology. This is what we envision, like with the mass production, in terms of just for manufacturing such devices. We may have, as you can see there, pin diodes, reflector arrays. This would affect a lot the overall cost for the device, for the prototype. But of course, going for a huge number of items, that will not be 1,000, will be much more, we can really reduce such cost. The point is, this will just cover that part here. As you can see here, we have very limited cost for manufacturing. So just for building the RIS, for building the device, the hardware, and would be the first, second, and third layer in this nice picture. In case we may have something a bit more expensive, in case you want to like device energy harvesting module, or like control, some advanced control on the configuration phases. But then what is like still something expensive is this part, this green big box here, which is the cost for installation, maintenance, and so on. So where to place the RIS at the moment is the relevant cost within this nice picture. So you can create a sustainable hardware, but still we need to find a way to install it, to like sell it, because that's the first point, without really affecting the overall cost. Of course, one solution could be just to go for like private environment, like putting at your place, like in an indoor, on your wall, just to improve the indoor signal coverage, or in a kind of smart factory where they will not pay for this. But going outside, going for something that will be like fully deployed, as also Orange and Intui said before, can be seen still as like a bit far away. Okay, and this is basically our evolution. We are at the moment there. We have these nice prototypes, reflector array. We are moving now, designing currently what we call passive sensing RIS, and we'll show you in a while, which is a new kind of device where we are adding sensing capabilities to the RIS. And we are also now currently devising the millimeter wave one. Why millimeter wave? Because once we move toward the ISAC concept, the ISAC landscape, of course, it's like impelling to start considering something between 20 and 30 gigahertz, because we need a kind of direct transmission while trying to get very narrow band. And of course, this cannot be done easily using a sub-6 gigahertz RIS. So this is the first motivation while moving toward the millimeter wave one. Of course, this would require a different kind of cost analysis in terms of like building, manufacturing, and so on, because using pin diodes, here you have a lot of antenna elements, patch antennas, and so on. Here, the cost, the overall cost will not be so negligible like in the previous case, but still could be something good when like comparing this with active base station. Definitely. Of course, here we have an operator we can ask, but usually like an active base station can be powerful, but will require a lot of money before getting like deployed and fully working. I've just like briefly described this, but as you know, again, this is the picture. This is what we have been doing. This is the RF switch. This is the antenna feeder. We have different flip-flops just to configure each of those bits. And then we can do this for each of those antenna elements. In our case, we have 256. But the main point is, since we have all of these combinations, so the code book would really explode because we have something like 7 power to 256. Basically, the idea that we had was just to reduce the number of configuration available. This was not updated because now it's 7 power to 256. Just to reduce the number of combination and configuration available in order to get a kind of optimized code. This, of course, would require, I would say, a new research line just to understand, because what we understood just using or just testing our RIS within some real environment is that the code book sometimes depends on the environment. So it's environmental dependent. Why? Because, you know, we have, again, all those configurations, so we may need to cut down and reduce significantly the number of combinations up to few hundred. But in order to do that, in order to avoid to just like remove relevant configurations, we really need to understand where the RIS is deployed. And this can be done after, I would say, a really advanced kind of code book optimization process. This is what has been done in terms of like measurement and testing. This was in an anechoic chamber just to test the sub-6 GHz RIS. And this was in what we call reverberation chamber. This was done within the RIS-G project that was over last December 2023. And basically, we have been doing different experiments showing that even with a sub-6 GHz RIS nearly passive, so there is no active components on that, only the microcontroller unit is the one consuming a little bit of energy. Basically, we have, as you can see there, some difference between the best RIS configuration and the baseline. You can also see, I think here, yes, the gain over absorption mode. Again, this absorption mode is what I explained you before. So when the RIS is set to like absorb all the incoming signal, we call it absorption mode. It's a kind of like assuming the RIS switched completely off. Here, of course, the difference, as you can see there, is between 7 and 5 dB, but we are considering, again, here, a reverberation chamber, where everything is quite chaotic, as you have seen in the previous picture. And here it's just changing a bit the setting, using a different antenna, and so on. But still, we can see some difference, even just using a nearly passive smart surface. So, of course, if you are interested in this kind of results, everything is now published, and you can find the deliverables of this RIS-G project.
NEC powers.
Sorry, I think we can remove. And then I wanted to show you if it's possible without the audio. Yes, what has been showing in at SEC last year, again with the nearly passive RIS. This was a kind of open environment, so full of people going around. So no anechoic chamber, no like advanced transmitter and receivers, no horn antennas, but just simple isotropic or dipole antennas. The RIS was there. We had just the monitor showing the results. This was the previous version, 10 by 10 elements. So this is just 100 elements in total. And basically the idea here was just to show that even in this kind of let's say, not control at all environment, we could get some interesting results. So basically we're just moving at runtime the RIS, the receiver, in order to be aligned with the RIS. And then what we did was just to make our optimization algorithm adapting dynamically the configuration of the RIS in order to get the best performance while moving it. Now you will see this. Now the guy will just switch the RIS off, and now you will see something going on there. Yes. And then once the RIS is activated again, you will see something change. This is just to like prove that even in this kind of chaotic environment, again, this was like a conference hall, so full of people going around, we could get, just using simple devices, something working. We could really see some different terms of gain. I'm not gonna like bother you with all these details because I think we are a bit late. So basically the idea was just to start thinking how we can really improve the RIS, adding some limited sensing capability. And the idea was just to add to the usual architecture something for the power detector. So the idea is to change the configuration dynamically, get for each of those like the sense power, and then detect autonomously which is the best configuration for the RIS. This means that for that specific direction or configuration of the RIS, we could find, for instance, a user or a transmitter. So this was done just to add practically a very limited sensing capability to keep again the RIS like nearly passive, but this would add additional feature to this device that then could be reused within the ISAC landscape. And this is how we can realize it. As you can see there, we have some like hybrid coupler, just getting all the signal. And then this is that, this is just used as input within this power detector, a passive power detector installed, embedded on the device, on the RIS, in order to really get putting together, as you can see there, communication phase and sensing phase. We can use the same device to do both things. Of course, you can decide whether to do this like in a sequential way, like over time, or whether you want to do it like spatial diversity, like selecting some of the cells for communications and some of the cells for the sensing part. And again, this would open up like several use cases, several applications, and several research lines on the optimization of that. And this is what we also envision in terms of millimeter wave RIS design. Basically, the idea would be to start thinking to use pin diode again in this way, like that the pin diodes can change, can apply different phase shift to each of those patch antennas, very limited patch antennas. And this is what we expect to get, something around 27 gigahertz. Because here, at this frequency, we are selecting that one because it's a kind of licensed frequency that could be like used with like different European operators. But of course, we can move with a slightly different design between 20 and 30 gigahertz. If I have some time, I would like to show you this nice video because this is what we have been doing within the RIS-CGG project in terms of sensing and communication. Basically, we have been using here in RIS to start devising localization and or positioning operations within a smart environment. In this case, it was Fiat. Let me remove the sound. So basically, the idea was to exploit the existing infrastructure within a smart environment like the one in Fiat. Fiat is a car OEM from Italy, placed in Turin, in Orbassano, where they already had a kind of 5G base station. 5G base station operated by TIM, Telecom Italia. This was just used to provide like connectivity services within this smart environment. What we have been doing was just to add two additional millimeter wave RIS provided by, as you can see here, yes. This is the 5G base station. by Ericsson, operated by TIM, and we added 2 different RIS provided by Greenerwave that we've been using and operating, sorry, at 27 gigahertz. So this was a 5G base station operating at 27. We had 2 RIS operating at 27, and then we had this, what we call CPE, or like commercial UE, that was just attached on board of this AGV moving around. This was like the area we would like to use as target area for localizing that specific AGV. Basically, the idea was just to use the connection between base station and UE that was not done using a line of sight, but was just a reflected path through the 2 RIS, and then combine the 2 information coming from the 2 RIS in order to localize, in order to get at runtime where the UE and the AGV was placed. I can just go a bit faster here. Here you can see this like 9 positions, and then this was the first RIS perspective, where we could really select the best one, which means the highest received power. And then for the second one, we did the same, and you will see in a while, with the, yes, in a while you will see the other one exactly. And we select even for the second RIS, which was the highest signal gain. Then we put them together, and we could really detect where the AGV was at that specific time with an accuracy of really few centimeters. So again, this was done using a commercial deployment, commercial base station, commercial UE, that was not there for localization, but we just added 2 RIS to deploy to start thinking how the ISAC can really go or enter within a smart factory environment. Let me go a bit faster now. Again, this was done in collaboration with REN and Train Station, SNCS, and Orange. This was only for coverage using RIS, rather than installing an additional base station in this kind of communication net zone area. What we did was to add different, at least from the simulation perspective, RIS that could really improve the coverage without incurring in the old cost required by an additional third base station. And then we did this kind of, I would call it integration test with Telefonica, basically O2 in London, just reusing some of their like data set. Basically, the idea was to reuse all the data we had for a specific area, as you can see here in this red square, and then we could really do a kind of cost analysis for a RIS-based network. The idea here was to compare, as you can see there, pico, micro, micro with IAB and massive MIMO base stations against 2 different RIS. And then we could see, we will see here, basically, a 40 by 40 and 80 by 80 RIS. Again, this was just a kind of synthetic traces that we could reuse in order to get some nice information. And we could really see that implementing, of course, with the total cost of ownership very low for the RIS, an 80 by 80 RIS there could be, in terms of performance, even comparable or higher than a picocell deployed by the operator. And this was a great result because we can really see how the RIS can start replacing, or I would say complementing and assisting, the existing network infrastructure. I think I don't have so much time. I had some nice research topic, but I will just spend perhaps 5 minutes, if it's possible. So basically, there are several research lines that we can still try to explore within the smart surface, RIS, and the ISAC world. This is what we call basically opportunistic ISAC. So the idea for this kind of activity or direction would be to, rather than devise and deploy a new hardware, a new device capable of like delivering additional services like sensing, We want just to reuse whatever is there, which means a device that is able just to improve the coverage or the communication capabilities of a network, of a system, like within a specific environment. And then we can reuse all the information we get in terms of RIS configuration to do what we call opportunistic ISAC. So the device is not there, it's not deployed to bring ISAC features, but we can reuse using AI, and now is when the AI comes to play. We can reuse all the information coming from the device configuration in a smart way. And we can detect, infer, where the user can be located. This is the reason why we call it opportunistic ISAC, because it's not an explicit ISAC, but it's something that we can do in an opportunistic way. We have been doing several tests and activities on this, but the paper is not public yet, so I will just stop here, and then I will show you this other nice work that is what we called sustainable RIS or MARISA. Basically, again, this is a way to start deploying within the real physical device limited sensing capabilities. This was done because we envisioned this kind of RIS deployed everywhere. So people without any expertise, any technical skills, can go to an electronic shop, buy it like a router, installing at home on a wall, and then activate it. The RIS is able to autonomously start detecting where users are and improving the overall condition quality, like signal quality, within an indoor environment. This, of course, would be out of control of the operator, and the operator might not be really happy, but we can see a kind of licensing or soft control, I would call it, on the RIS to still make operators happy, to have everything under control. Sorry. Then, of course, toward this direction, we can also see something towards what we call autonomous, completely autonomous RIS. And this was something that I mentioned at the beginning of the talk, where the RIS can also be equipped with some harvesting module. So while having this kind of self-configuring RIS that everybody can buy and installing at home, we can provide the RIS with a kind of harvesting module. Of course, if you're expert in this, usually the energy that you can really get captured from kind of harvesting module are very, very limited. So of course you might need kind of battery power RIS, but still this is something that could be built within a real device. Then of course there are several applications also looking at what is called NTN, or non-terrestrial network, where the RIS can be placed on board of an HAP or UAV, just to improve this kind of conditions. Yes, and then this is also something very interesting, because this was more or less linked to what Dintui and Laurent said before, the bandwidth of influence. This is one of the, I would say, most interesting feature of a smart surface, because sometimes if the bandwidth is very large, an operator wants to deploy a set of RIS for their specific license bands, there might be some influence, some impact on the other network infrastructures of the other operator. So having a kind of very narrow band RIS or frequency selective RIS would be really important. In this kind of research line, what we tried to do was to have a kind of dynamic RIS. So a smart surface that is able to change, to jump from one frequency, one specific frequency to a different one, without really changing the other design. As I said at the beginning, usually if you want to have something operate at a specific frequency, you need to design with a specific distance among the elements. Sometimes you can go below lambda over 2, doesn't matter, but still you need a different design, different layout of the RIS. Here, the idea was to start thinking whether you can have a kind of flexible RIS, able to cover different frequencies, able to jump, for instance, from sub-6 gigahertz to millimeter wave. And then this is also quite interesting because this is in line with the operator view. Basically, having a fully deployed RIS network can really impact on the performance of an existing cellular network. So there might be a kind of need to optimally configure base station while deploying the RIS, because the RIS can really have disrupted impact while being like activating on the base station performance. So we must need a kind of, we are also working on what we call in-band control of the RIS, where the base station can like somehow control the RIS, even though it's not aware of it. But still, there is an impact that we should take into account while designing and deploying RIS. And then I think I will just show you this last nice picture, and then we can stop. This is what we have been doing within, again, the RIS project. This was the first attempt, and as you can see there, this is 2021, but still we had like some refinements of a kind of architecture ORAN compliant. So how we see 3GPP, ORAN, and RIS working all together. Why is this important? Because in a kind of what we call smart radio environments, where the RIS will be a kind of new node, new system node, this kind of interaction between the RIS controller and the network controller is like important, but it's also very challenging. And this is how we like see it. Again, this was a kind of tentative picture, has been refined many times, but basically the idea here is to have a kind of controller talking perhaps with the near real-time RIC from the ORAN architecture, or even having some hardware talking directly with the CU or with the DU, in case you are expert, of course, of the ORAN architecture and all these components. So this kind of interaction, those interfaces that you can see here, of course, do not exist at all, but we are trying to start thinking, designing, and also discussing how those interfaces can be added within the ORAN architecture. What is missing there, and something that again is under discussion in ORAN, is what we call also real-time RIC, that is not there, but that can play a role within this nice picture. So yeah, I mean, I also have some other nice like research line and theory, but just to close, this is, in my opinion, the takeaway message. So basically, the 6G era is coming, and ISAC will play a role there. So it's very important for us starting thinking whether the smart surface can be the key enabler within this ISAC landscape. We can have like what we call openness, because we have seen that can be directly integrated within the ORAN architecture. We can have nearly or fully passive devices at very limited cost and with like smaller carbon footprint. Everything would go toward the sustainability that again is one of the impelling like challenge for the 6G network. But still we have a lot of things to do from the theory and also from the implementation perspective to make like the RIS smart surface able to really start thinking whether ISAC can come into our existing network infrastructure. So thanks a lot for your attention.
one short question, just one.
Hi. Thank you for your talk. Actually, I had two questions, but I'll do at least one. Yeah. So going back to the examples of RIS you've shown, what is obvious is that the size of this RIS is quite small, the prototype you made, and the number of elements is quite small. What I'm sort of interested to see is that, and maybe you can already answer that, is the type of a study that would, so when you had this in a booth, then arguably you had it in the near field of the transmitting antenna, in fact, so it's very close. What for me would be interesting to see is a kind of study that addresses what is the size of RIS would be required in specific scenarios such as train station, because we talked about the different installation projects, smart factories, train stations, and obviously it's not a one size fits all kind of situation, is it? So what kind of size you would need in and what's the dependency on aperture efficiency and things like that?
Yes, that's a very interesting question. Thanks, because I didn't mention this. Basically, this is around 40, 50 centimeters by 50 centimeters, a bit less. We designed this way because it's, fully square, so you can like combine multiple RIS to create a larger surface while keeping the interdistance among these last elements and the first one of the next one, again, equal to lambda/2. So this design was done like in view to get a larger one, just combining more. The one that we've been testing in at SEC at the conference was a bit smaller than this, was a bit less than 40 by 40, but again, it was in near field, so was like sufficient to get some results. In the smart factory, which means Fiat, we've been using 2 RIS at millimeter wave, and the size was, I would say, something like a laptop, so an A4. But in that case, the RIS was with the 1,600 elements, because this was 27 gigahertz. So the interdistance and the patch antenna size is very limited. But again, even there, so with this kind of size of RIS, in that case, was not really near field, but we could get some results, at least from the localization and positioning perspective. Deploying this kind of equipment outside, of course, would really require larger surface. But this, again, depends a lot on the frequency. But of course, you cannot install a 40 by 40 centimeters like on a facade on a building with the hope that, at some point, some signal will come from the base station and will be reflected properly. So in that specific scenario, so I would say outside, you would need, even with UAV, as I was showing before, you would need something around 1 meter by 1 meter at least. But this kind of test, of course, we didn't test it yet. We hope to get it once we get the millimeter wave one working, and see there whether the millimeter wave frequency can really have a huge impact on the sides. But definitely this is one of the main limitations of this technology nowadays, to have it implemented everywhere, like outside. Thank you.